Professor Turney is an internationally recognized earth scientist and research leader in both climate and environmental change from the tropics to the poles. By pioneering new ways of combining climate models with records of past climate change spanning from hundreds to thousands of years, he has discovered new links between variability mechanisms in the Australian region and global climate change. Professor Turney, congratulations. I invite you to present your talk entitled Using the Past to Understand and Plan for Abrupt Future Climate Change.
Thank you very much. Thank you. And it's an incredible privilege and honour to be here today, and particularly receiving a Frederick White Award. It's remarkable just how much support we get in Australia from all different sorts of funding agencies, but I'd particularly like to acknowledge the Australian Research Council through their work from various funding agencies, grants we've had, and my Laureate Fellowship. A lot of this work wouldn't be possible. And I think also it's important to stress, as many of my other co-speakers, how this is a huge group effort for so many people, and be very privileged to work with some fantastic individuals, not just in Australia, but globally as well. So what I'd like to talk about just shortly is using the past to try to get a better handle on future climate change, and particularly with regards abrupt changes, those situations where the climate system has shifted from one state to another. We're looking at some examples of that. Or maybe not. Sorry about this. Okay, thanks, Dominic. That's fine. I tried that one. Oh. Dude, go on. I failed the technology test. Sorry about that, ladies and gentlemen. This is not good. That's now. There we go. Go on. That's bitten into my tongue. Right, you're probably familiar with variations of this. This is basically showing global temperature changes from the mid-19th century. And traditionally, we talk about warming since the mid-19th century, the pre-industrial period, on average about 0.8 degrees centigrade. But this rather wonderful animation from NASA shows how spatially complex that is. And from about the 1950s, you see this lovely warming. It cools off again in the 60s and 70s, and then ramps up into the 80s through to present day. You can see, though, in particular, some areas seem to have this enormous warming in some key areas. Quite dramatic. A lovely example of that is just here in the Antarctic Peninsula as one particular area. So what we're interested in, though, is how we might be able to use the past to reach further back. We heard earlier today we've got limited observations in many areas, particularly the Southern Ocean. And if we rely purely on observational data, we can get back 150 years or so. If we rely on satellite data, we're only talking a few decades. So what sort of thing can we use? Well, one possibility are trees or tree rings. This is one example. This is Dr. Jonathan Palmer. He's one of the members of a team standing next to ancient kauri from Northland, New Zealand. These are phenomenal trees. They live up to 2,000 years. They're buried in peat bogs for over tens of thousands of years. And they preserve a year-by-year record. Much like many of you, I presume when you saw a fallen tree, you'd look at the rings. They're annually resolved, even many Australian species. You can try and count how many years that tree has actually lived for. But that thickness of a ring is actually an indication of growing conditions, and big, thick rings indicate good, strong growing conditions that you can calibrate against climate. This particular example is around 52,000 years old, and it lived for 1,100 years. So just one example of the many that we're working on. You can use lakes and peat bogs as well. This is Lynch's Crater in tropical Queensland. 2 weeks spent in a swamp. This was the brief bit of light we got. We actually got a rainbow there. But this is working with many PhD students and colleagues at Monash University. 65 metres and going back 250,000 years. And with new analysis techniques, we can get down to decadally resolution that we can reconstruct environmental changes. Likewise, we can actually go to Antarctica and also get different handles on climate and the environment there as well. This is from one area, a blue ice area called Patriot Hills. If anyone saw Palin's Pole to Pole, some years ago, I'm showing my age now, where he took off for the South Pole, that blue ice runway is our site. So Palin couldn't go to the pole from where we are now, unfortunately. But this ice effectively is welling up from deep below the surface. So by effectively walking across the surface, you're going back through time, over tens of thousands of years. And the beauty of that is not only can you take a lot of detailed analysis using equipment you can buy from a hardware store, which keeps it really cheap, relatively speaking, you can also take large samples to analyze for gases, the air trapped in the samples, to actually reconstruct greenhouse gas levels for multiple species at the same time. This is some work we're doing with CSIRO. So let's have a look at one potential analogue for the future, the last interglacial. This was a period between 130 and 115,000 years ago. It was a period when the planet was just a little bit closer to the sun. Work we did some colleagues in the United Kingdom pulling together data sets and actually doing the first reconstruction of how much warmer was it. And when you put all the numbers together, you come up with about 2 degrees centigrade warmer than pre-industrial temperatures. Now, that's important because that's a sort of target, a minimum target that we aspire to keep global temperatures down to, of course, higher greenhouse gas emissions ramp up to reaching 4 degrees plus. Importantly, though, it's not just the temperature that's significant. In particular here, what you have is changes in the rate of global sea level rise, just on the upper panel here, and actually the amount of global sea level. And the important thing is the classic definition of the last interglacial, shown by the red box there. Before that, you've got a magnificent increase in sea level rise, quite stupendous. But the practical upshot is that you have between a 6.5 and 9.5 metre sea level globally averaged higher than present day. So the implications from the last interglacial is if we sit the planet at 2 degrees for long enough, we'll sit at 6.5 to 9.5 metres higher than present day. Working with colleagues at University of New South Wales, running the UVic model, we wanted to see shifting the wind south, what impact that might have. And what we see from this 135,000 years ago are these areas of warming off key sectors of Antarctica. And working with colleagues in the University of Victoria, running an ice sheet model, a PISM, you can see large areas of the East and West Antarctic, which are highly vulnerable. That's significant because using projections forward, shifting the wind south, what we see is actually similar areas of warming happening by the mid-21st century. Now, how quickly the Antarctic ice sheets respond is still uncertain, but just a couple of weeks ago, NASA announced that the Amundsen Sea area, where the red box is here, the Thwaites Glacier, is now irreversibly melting and will probably be into the oceans in a couple of 200 years or so, with a global sea level rise of about 1 metre. But we want to put this in a bigger context. There's big changes already happening. We've seen in Southwest Australia, Perth, a shift in the mid-1970s, a drop in winter rainfall of around 20-25%. We've heard about shifting winds. We want to get an appreciation of what impact that has had in different sectors, and also whether we're detecting these abrupt changes already. So last year, a colleague, Dr. Chris Folger, and I decided to lead an expedition to a region where it's not very easy to get access, taking a large multidisciplinary team of all the way through from the natural and physical sciences down to Antarctica, called the Australasian Antarctic Expedition. And a major component of that was actually public outreach. So not only reporting what we were finding as we went, but also showing people how science works. And if you look on Google or YouTube under Intrepid Science or under Prof. Chris Turney for Twitter, regular daily updates, including with Hangouts on Air with Google, real-time interviews from the field. I'll just show you some results from this. This is Chris here, showing a short call we took from one of the sub-Antarctic islands. And we were trying to get particular focus on the trees themselves. Unlike the kauri, which are enormous, this is Dracophyllum, just here in the background. And a regular hazard on these islands was the local wildlife. In fact, we spent half the time running away from these beasts through the undergrowth. But now and again, we get time to actually sample those trees. And Dracophyllum is one, the main species there, annually resolved tree rings going back about 150 years, an area where we only have limited observational data, and it's highly sensitive to climate. The beautiful thing is it's also collecting, absorbing carbon from the atmosphere, so we get a hand on the carbon cycle as well. When we plot the data up that we've generated, this was only collected a few months ago, we see a step shift happening in the mid-1970s. Supports local observations already, but we go all the way back to the mid-19th century, and we're working this up at the moment. There's a wealth of other data being generated from the expedition, huge number of firsts for the region, including the first terrestrial glacial limit constraints for 3,500 kilometres. So that's all really very exciting, which we're just building up. So just to finish off on my last slide, the future, basically what we're putting together now is a wealth of data where we're actually trying to extend the observational records in key regions using natural archives. We're exploring the sensitivity of carbon feedbacks. We're closely integrating the records of past change with climate models. And we're also using this targeted response of small science, getting the public engaged to actually fund strategic questions in key areas. And finally, a big thanks to all family and friends who made this work possible. Thank you very much.
Thank you, Chris. Are there any questions or comments? Obviously, everybody is hungry. So these beasts, which you have to really, you really, how do you deal with them?
Run away, actually. The sea lions, they hide in the undergrowth, and a lot of the time that bush is remarkably thick. So you're there with heavy packs, all the gear, and there's a team of you, and basically on all fours. It's not very, it's quite humiliating. And then all of a sudden you'll hear this hot breath, and there's this face right in front of you, and everyone's backing away very calmly, trying to look manly, of course, at the same time.
Okay, on that note, could you please join me to thank Professor Turney?
Thank you. Thank you very much.